gas particle flows in a horizontal channel. Thank you very much. It's Nicholas Caballé.
Oh, I see. Thank you for organization. Is it working? Yes. Is the microphone working? Okay. So I'm speaking about biphasic flows, and so I have a mathematical point of view, but you'll see I have also numerical results. I'm working in Clermont-Ferrand with Laurent Chupin, which is a mathematician, and Karim Khalfoun and Olivier Roche, which are geophysicists. Okay, so the main purpose is to understand why such a pyroclastic flow is going very far from the starting point, and especially also from the bottom, even if the landscape is very flat and horizontal. So that's the main purpose. And what I'm interested in is not all the smog all around here, but the dense granular flow which is under that and which gives that deposits. Okay, and my goal is just to have a mathematical model for a new rheology. So let's have a look on some experiments which are a little bit simpler than the real case. So that's the collapse of just a grain column. And if you do the same experiment with a column which has been freediced initially, that means that you inject some gas through the column, then the result is that one. So that could be a good reason how to explain the long distance run distance. So let's compare both. So the second one here is my I'm interested in that second experience. Okay. So now I'm just describing my model and then show you some very recent results which are numerical and theoretical. So let's begin with the model. This is a continuous one. So this is based on Navier-Stokes equations. But here I have two phases which are particles and the gas. Okay, so if I put that in Navier-Stokes systems, I have two of those which are coupled. And if I want to use this in a numerical experiment, this is very too complicated to solve, especially if I want later to use it in a three-dimensional case. So that's why I'm simplifying it. I want to simplify it. One way is to consider only one mixed fluid, but with a variable density. Okay. And then the equations are the following one. This is incompressibility. This is mass conservation in the mixture. So these are the mixture property characteristics. And this is the momentum conservation. Okay. And then parameters are the following ones. So velocity. V, P is the total pressure. And rho the mixture density. Other constants are mu, the viscosity here, and the standard gravity. So those are already known in mathematics and physics, but not very good for my purpose. So I have to complete it with an appropriate rheology, and that's what I'm doing now. Just recall that this is there is no depth average here, so no shallow water theory, but it could be done later if I want. So let's have a look on the rheology. This is based on two main ingredients. One is the solid friction law, okay, and the second one is I suppose I know the gas behavior. So I will give you those two ingredients now. So let's have a look on the friction law. This is the granular bed, which is fluidized. Let's have a look on two particles. So this is discrete for now. If the upper one is going faster to the right, then there is a friction constraint which is oriented to the left, okay, and which norm is proportional to the normal constraint, which is the solid pressure here. But in my case, I have a continuous model. So I have to write it like this. This reads if the vertical variation of the horizontal speed is plus, so the gradient is like that, okay, then the shear tensor has a contribution on xy, which is minus a coefficient times the solid pressure. Okay, so the coefficient here is the tangent of the friction angle. We can discuss it at the end if you want, if you like. But here PS, I don't know anything on PS in my model, so I just put P minus PF, which is P is total pressure, which is already in my previous system, and PF is a new unknown parameter, and this is the interstitial fluid pressure. Okay. Now let's write it in 2 dimensions, or 3 if I want. The shear tensor is just this constant times P minus PF plus times this matrix of signs. Okay, this is only the non-isotropic part, because I have already the isotropic part in my system. Okay, so let's have a look on the gas behavior. I just refer to the empirical diffusion law, which is this one. So this D is just the hydraulic diffusion coefficient, and which is empirical, and then this term is just the transportation or advection term, and that closed my system. Okay, let's sum up. This is the non-homogeneous incompressible Navier-Stokes equations, in which I add my specific rheology. So this is the friction law, in which PF is playing a role and described like that. So that's the complete model, and so I don't speak about the boundary conditions here, but if you have some question, I will answer it. Okay. Okay. Now I just show you some very recent numerical results. This is only the collapse of the column. So initially, this is fluidized. Okay, totally fluidized. The column is 40 centimeters high, and all quantities are here. So we will discuss this later, okay? So let's have a look on the movie. So the behavior looks pretty good at the beginning, but as you can see, there is a problem here at the interface, which is very big, and then the flow is quite good, but a little bit too long. So this is only 1.5 seconds. So comparing to the 10 seconds on the first movie, this is not comparable. Okay. So here, just to say, this is the color are just for the density, which this part is for the gas, this is for the grains. Okay, so when I'm looking at that, I wanted to explain why. To explain if I have a solution or not. So, as a mathematician, I have to prove some existence theorem. And at the beginning, this is very recent, and I have begun with that system, which is simpler because there is no density here. So rho is equal to 1 everywhere, and no fluidization neither. But there is that term, which is one new complication on that system, and I have proven that under that assumption there is a local in time solution, and that assumption is just that phi, that quantity, must be small enough. So that's really a problem when I'm dealing with physical flow. But what I would like to extend my theorem to the complete model to see if that kind of assumption still stay in my model, and also extend that theorem to physical boundary conditions, because this is not the case for now. Okay, about the algorithm, I would like to deal with the problem of phi, which should be around 30 degrees, and I can't choose phi bigger than 10 degrees or something like that for now, because of a problem of stability, numerical stability. And I would like also to deal with the numerical diffusion, which is at the interface. Okay, and then perhaps have some improvement on the model itself. For example, D depending on P or rho, or including collisions. Thank you for your attention. Perhaps, okay, yeah.
A little bit technical question. Can you go back to your existence theorem?
Yeah.
So, you assume that your initial condition is H2,
Yeah.
and it's not divergence free,
Sorry.
and it's not divergence free.
No, it's
No?
H2 sufficient.
That's quite surprising. Okay. And I suppose then you prove that your solution is classical.
Yes.
Let's speak about local in time. Is it a classical solution or a weak solution?
It's a classical solution in weak. Yeah. Perhaps we can discuss it. Sorry.
Yeah, I just wanted to know why the form of the extra term. How do you know if it needs to have that form? The extra term,
Yeah.
the one in blue.
Sorry, I haven't understood. What's the problem?
How do you know that the extra term in blue in your
Yeah.
equation has that form? Because
Okay, yeah. Because I have it in my model now. So replace just sigma by that here, and put tangent of phi and before the divergence. So this is all. Or perhaps I have forgotten P.
Granular feature.
No, there is no P here. So have I answered the question? Not sure. I can't see what's the problem.
No, I'm just asking.
Sorry. Yeah.
Charlie?
Just one quick comment, and this is only for historical purposes.
Mm-hmm.
But the mechanism of fluidization for lubricating long run-out landslides goes back to a paper I just had to look up by a fellow named Kent in 1966. You might want to reference that for historical purposes because he's a geologist and he just says, how about the thing is fluidized? And that's how it worked its way out, and that was about all the physics that were involved in it. And the and I doubt there was equation in the whole paper, but it's probably worth noting.
I've got a question for you. It seems a bit strange to put a diffusion equation in for pressure.
Yeah.
Because you'll get exactly the same behavior in water or something, and it's completely incompressible. And physically, what's happening is there's a slip velocity between the solid phase and the liquid. The particles are sedimenting, and it's very hindered sedimentation. And then the pressure's determined by an elliptic equation. So it's a prognostic. It's a prognostic, not a diagnostic equation.
Yeah, but so that analysis is just to see if we can choose some like a behavior, like some term to describe the behavior or the change of behavior from the liquid one at the beginning to the solid one at the end on the solid part. But it seems to be good for the liquid part, but for at the end it should stop with an angle, or which is teeny. But if I just show you some experiments with a bigger phi, which is around 10 degrees. So this is not fluidized, and this is not stable numerically, but this is stable and fluidized. But you can see this is the same behavior than at the beginning with another angle, but this is different from the first one. So if I want to describe my evolution with that kind of rheology, it should be good also for that non-fluidized one. But Navier-Stokes equations are not good for that behavior, which is solid.
I will make a comment to your question. I think that fluid pressure, this equation that he uses, is sort of an order parameter. It introduces an order parameter, and you end up like with cantilever fluids that you introduce. This explains, at least to me, as I see these equations, how this parameter emerges with this sort of equations. I mean, at least intuitively, as I see it, that would make sense if you introduce it as an order parameter.
Maybe, Michel?
Yeah. When you take some coffee and that's partially vacuumed and you open it up, you do have a diffusion of pressure. It goes as the permeability times the mean pressure over the viscosity. So there's a diffusion of this in the compressible system. But the question I had is, within that equation, I know there's this Tarzaghi approach, which consists of subtracting from the pressure in the granular system the pore pressure. But I never quite understood what that means, because in principle, the fluid pressure should integrate to an Archimedes buoyancy like force. So I don't understand why we put it in the constitutive law, in the frictional law that way. I know the solid mechanics, they do that all the time, but I just don't get it.
I understand your remark. This is just a mathematical way to deal with some remarks which are physical. But yeah, you're right. This is not physically correct. That kind of it, because this is not directly derived from a biphasic model. This is really another one, which is one particular point of view, and I'm just looking at this to see if it's good or not in terms of that behavior. So.
Okay, let's thank the speaker once.